This is a technical explanation of root detection and the differences between heuristics and hardware checks. It is intended for mobile application developers, software engineers, or anyone interested in a detailed exploration of the subject. Heuristic root detection does not determine root status at the OS or kernel level. Instead, it evaluates observable indicators of a modified operating environment from the perspective of the app. These checks run in an application context and look for signals such as elevated process capabilities, altered system behavior, or the presence of tooling commonly associated with root access. While root itself is a device and OS level state, heuristic infer that state indirectly based on what the app can observe at runtime. In the early days, heuristic root detection could be as simple as checking for the presence of a specific binary or application. Over time, this evolved into more advanced techniques such as probing system APIs, detecting indicators of process patching in memory, looking for system-wide artifacts left behind by routing tools, and using side channels to observe deviations in OS behavior. Heuristic checks are based on assumptions about deviations from normal system state and behavior. Modern tools can hide or alter these signals. Attackers can, in some cases, bypass heuristics without actually removing root access. Hardware-backed checks provide a stricter form of environment integrity checking that is based on attesting the device's trusted key storage locations. This allows you to verify that the device's secure key storage, boot chain, and operating system have not been altered or tampered with. The device generates cryptographic proof using hardware-backed keys, attesting that said keys are bound to secure hardware and that the device boot process has not been tampered with. This includes measurements of the bootloader and operating system that are anchored in device's trusted execution environment and secure elements if available. This hardware-based check can prove the lack of OS-level tampering, which otherwise cannot be reliably observed from within an application. Hardware-backed integrity checks provide a strong and trustworthy signal because they originate from components that cannot be modified simply by unlocking the bootloader or altering the software environment. The trusted execution environment, or TEE, and the verified boot chain operate below the operating system and are isolated from a normal application code. This means an attacker would need a genuine exploit, often at the firmware or a hardware level, to tamper with them. As such, hardware-backed measurements are far more resilient than application-level observations, which can be bypassed or manipulated on a compromised device. By relying on a hardware-backed trust rather than app-visible heuristics, these checks offer a level of integrity assurance that is significantly harder for attackers to subvert. They allow an app on backend to reason about whether the device is in fact bootloader locked and in an expected OS state. At the same time, this signal is not immune to attack. There are real-world techniques that attempt to spoof or intercept hardware attestation results by emulating TEE responses in software or relaying valid key material from other devices. In these cases, the integrity signal itself becomes the target of this attack. Because of this, hardware-backed checks are most effective when complemented with heuristic signals that help detect anomalies or inconsistencies around the attestation process. This is especially true on devices where newer protections are unavailable or where the trust chain may be partially compromised. Since hardware checks are a very strict way to ensure the integrity of the environment, they are not suited for every situation. Not all devices support hardware-backed attestation equally. Older devices, devices made by certain manufacturers, and devices running non-GMS certified versions of Android, such as those running custom ROMs on devices with a relogged bootloader, could have their hardware attestation results signed under a different root CA than Google's. Some devices may also produce incomplete or no results at all due to the lack of support for hardware attestation. Non-GMS in this context refers to devices that have not been certified by Google for running their app suite. Because of this, the device's TEE does not sign attestation responses under Google's attestation root CA. This means hardware-rooted signals such as TEE-based measurements or verified boot state could be unavailable, unreliable, or need to be manually trusted on an allow or deny list basis. As a result, relying solely on hardware backed integrity checks can lead to inconsistent coverage across the device ecosystem. Heuristic and hardware backed checks represents a different approaches, ranging from detection to proving a device state, each with their own limitations. In practice, the difference lies in what these approaches are able to observe and attest. Heuristic approaches infer a potentially modified environment based on observable signals, which means some compromised environments may go undetected. Hardware backed checks, on the other hand, provides a definitive statement about the integrity of the device and OS at the given point in time. In an ideal world, you would only want true positives and no false positives. In reality, the challenge is not that the hardware backed checks reach the wrong conclusion, but how these results are interpreted and enforced for a given use case. The value does not come from simply enabling both types of checks at the same time, but from how these signals are used within a broader risk and response strategy. For example, a bank onboarding a new customer may choose to apply very strict hardware backed integrity checks during biometric identity verification. If a user fails that strictness, the flow can fall back to a manual verification process outside of the app. In that same flow, heuristic signals can still provide additional context, such as detecting runtime tampering or instrumentation attempts that occur even on devices that pass hardware attestation. This allows strong integrity guarantees while still monitoring for application level manipulation. In contrast, other use cases such as mobile payment terminals may deliberately enforce strict hardware backed integrity at all times. The sensitivity of processing payments and the ability to mandate certified hardware justifies that level of control. In such environments, heuristic checks can still be used to detect anomalies around the attestation process itself or other runtime manipulation attempts, such as those targeted at the application, rather than the whole device. This is how heuristic and hardware backed checks deliver real value not by being combined mechanically, but rather by being applied strategically based on risk, context, and other action being performed. Many modern attacks do not require root at all. Repackaging, dynamic instrumentation, and logic abuse often happen on non rooted devices. Root detection should be treated as one signal in a broader risk assessment. Effective mobile security comes from layering signals and protections. Root detection, runtime protection, code hardening, plus threat collection and enforcement all work together to detect and respond to real threats, rather than relying on any single mechanism like root detection. Use root detection to inform security actions as part of a broader risk assessment. By understanding the strengths and the limits of heuristics and hardware backed checks, teams can apply proportionate responses such as monitoring, step up authentication, or restricting sensitive features instead of defaulting to a single hard decision.